Our speaker this evening has been amongst the core programmers of Postgres since 1999. Please give a great big round of applause to Peter Eisentraut.
Hello. Thank you. Thank you for having me again. So actually the 32 terabytes probably now with partitioning in Postgres 10, that's probably not even accurate anymore. So we're working toward extending all those limits. So today actually we're going to talk about sort of expanding limits of Postgres in other ways. So I'm going to talk about the work we've been doing in the Postgres community and in my company, Second Quadrant in particular, to extend the Postgres replication capabilities. So as Eric has introduced me, I've been around the Postgres project for 19 years now, so to speak. And I'm a committer in the Postgres project, and I work for a company called Second Quadrant. We are doing sustainable open source development for Postgres. All right, so a lot of you, who is using Postgres already? Just so we can see. Hands up. All right, 2/3 maybe? Okay, cool. So we think Postgres is, obviously it's a relational database management system. We think it's a general purpose database of choice for many people nowadays. Obviously, 99.99% is just something we made up, right? But obviously, there's database systems that have sort of more niche purposes or very specific purposes. SQLite is very popular for embedded use, and there's some databases that are very good at sort of maybe time series or things like that. But we think Postgres is a good choice for most applications, and it's also a good first choice if you don't know what to use. Start with Postgres, and oftentimes it will work out, right? And it's an open source. So there's a joke what's going around Twitter for a while. It's like does your application need a blockchain? Try it on Postgres first. If it works, then you don't need a blockchain. Oh, that is interesting. Can we fix that somehow? I don't know.
Not full screen.
What is that?
It's a PDF file, it's full screen.
PDF. Will is working on that. Is it full screen, Will? Hang on, I'll keep talking. Will is working on that. Oh, it's kind of scrolling. That's interesting.
Yeah.
Can you make it non-scrolling and just have it on full screen?
Do you hold the micro cluster too?
I'm sorry, I'm not too used to that.
You can actually turn it up on the bottom if you like. On the bottom of the mic, there's a little
Hello. This way?
That should be it.
All right, so this is, just remind me on the microphone here, I'm not too used to that, but so Postgres is DB Engine's database of the year 2017, right? So it's an internet poll, okay, who cares? But what is more important is that cloud adoption by the major vendors shows that it is important, right? Obviously, AWS has already been supporting Postgres in its RDS product for a while. Google and Microsoft started their cloud offerings this year, I believe. Actually, Google just started a month or two ago. And Microsoft is offering hosted Postgres now in their cloud, and IBM, I guess, is also still around. And Postgres was voted most beloved RDBMS by Stack Overflow by 60,000 Stack Overflow users voted there. So that's part of the fake that maybe the DB Engine's poll. So to be fair, actually, the poll there was for the most loved database, and the overall winner was Redis. So, but we think, I think it's fair to say it's not a relational database management system. So Postgres is the #1 RDBMS. Okay. And we are now at the point, or have been for a while, that other database systems are essentially copying Postgres, which is, I think that's a compliment. And unlike other open source ecosystems, also the Postgres open source product is is sort of still the main place where things are happening. There are some forks every now and then, and a startup is founded around them, but a lot of those have trouble keeping up really with the Postgres development. So a lot of those forks that were started a couple of years ago, they're still in the old versions, and they're having trouble keeping up with the open source development pace. So actually, a couple of the new wave of startups, let's say, or new companies that form around Postgres, what would have been a fork are now working mainly on or providing now extensions. You might have heard of companies such as Timescale or Citus. They're kind of very popular in the Postgres ecosystem, and they're now just exclusively an extension. They have avoided, they use the extensibility of Postgres, avoided forking Postgres, and it probably is going to work out better for them. So, yeah, and Postgres works for all these use cases and many more. Again, there might be a better pure full text search database, right? If you maybe like Elasticsearch or something like that. Or there might be a better, I don't think there is one, but there might be a better GIS database. But Postgres can support all of that, and the nice thing is it can support all these things together too. So if you have a database that's maybe some Geo stuff, maybe some JSON stuff, and you want to do some full text stuff and some traditional stuff, you can have all that in the same database and use all the other facilities that you have for backups and management and stuff. It's all the same. So that's kind of the nice thing, that you have one universal system that can support all these use cases reasonably well. So what we've been working on is essentially what this picture kind of shows that we're using for marketing, is that we want to put not just one database that can do a lot of these good things, but many databases in different places that can talk to each other, okay? So I'm going to explain more details about that. The product and project that we've been working on in my company is called BDR. It stands for Bi-Directional Replication. It's not really a good sort of fun marketing term, but it's kind of what stuck. So that's a multi-master replication system for Postgres. So you can set up a bunch of different database servers, and they can all talk to each other. And you can write to any one of them, and they all sort of sync each other up. So VTR1 has been in development for about 6 years, and it's been in production now for 4 years. So it's reasonably battle tested. And what we're now announcing, or have announced just recently, is VTR3, which is basically pretty much a rewrite of this facility on a new stack with lots of new functionality and features. Okay, so you might be wondering what happened to BDR2. That also existed briefly, but we kind of, while we were developing BDR2, we kind of figured we kind of got to reset and then do it differently. So BDR2 is kind of in use with a few customers, but we're not sort of pursuing that any further. And I'll explain a little bit later on why we changed that. So while BDR was originally intended for the sort of geographically distributed use case that we just had on the previous picture, it turned out a lot of people actually wanted to use it for something different, and that was for a high availability setup. Because that kind of also makes sense if you think about it, or it's sort of an attractive use case if you think about it, that you have all these different sort of databases here, and they all talk to each other and sort of sync with each other, and then if one of them goes down, you just use another one, and they all keep talking to each other. And that was a good idea. That didn't actually really work in BDR1, because the way BDR1 was set up is that all of these had to be able to talk to each other all the time, and if one of them died, then the other ones all kind of got upset. So that, for a variety of technical reasons, it was just not made for that, right? But to an extent, it got a little bit annoying that, in a sense, that a lot of people wanted to talk to us about BDR and explain the use case, and we had to tell them, well, it's not for that, right? So, what we did at the end is we just rewrote it to actually support that. So, and that's kind of probably going to be the most important use case from now on. So, this is how you might, if you're using any kind of replication at all until now, this is kind kind of the situation you might be in. So if you just, so up here, this square thing would be a client application. If you write to a database that's local to you, that happens pretty much immediately. Right? I did a talk last year in this series also that kind of explained what was going on here as you actually write something. And we had sort of the example that I used to, I think, was sort of 10 milliseconds for the whole thing. And you can tweak that a little bit. So you get this sort of 5–10 millisecond range of just a local command. And that's great. So, but when you then grow, across the country or worldwide, as a lot of us want to do, then you might start setting up web servers in different sites and so on. And then you have that situation where you have maybe let's say we're on the East Coast here, and then you set up another web server farm on the West Coast, but it's still writing to the same database. So you're just the latency of the link requires that then your write is going to take about 160 milliseconds or so. And then if you're going from that to Asia and Europe and all that kind of stuff, you're going to have hundreds of milliseconds of time for your client application to write to the database. And once you get into more than 100 milliseconds, you're at the point of sort of the limit of human perception. Everything that is less than 100 milliseconds is essentially immediate for a human experience. But once you go above that, humans will notice, and they think your stuff is slow. And so far, most people, either they don't use Postgres or a traditional database for this, they use something else, or you do a whole bunch of caching or queuing systems or things like that to work around to sort of write locally and then sort of work it out later or something like that. So, and that works. A lot of people have been doing that, but then you don't have the benefit of a real database system. Right? Then you just kind of fake that essentially and lose the benefits of the database system. And you have a more complicated architecture. So what we want to do is this: you just write locally. You set up these databases at all your sites. And we had that earlier picture of the globe. You can set it up in all these different locations, depending on how much money and effort you want to spend. Essentially, to set that up. Or even nowadays, you just click buttons and have different regions, right? So that's not even that hard anymore. And then you just write locally, and then you write into a real database here, and then the databases talk to each other and sort that out. So as I was mentioning, the two main categories of use cases we see for this is the distributed databases globally, or the very high availability architecture where you can have the same, so these multiple databases in the same location, in maybe different availability zones or something like that. And then you can, just when one fails, you just use the other one. And I'll show in a moment how that works. For globally distributed databases, or just distributed, if you don't want to go global, there's a lot of interesting use cases. Just the case of that I mentioned, you have clients in different places, and you just want to give them a good, fast experience. You also have this new or not so new buzzword of the Internet of Things, where you have a bunch of devices all over the place that collect data, and you want them to record that data somewhere, and you want to do that as fast as possible, so they all talk to your central database, so you can put different databases close to them and collect the data there and then consolidate it later. Or also the new thing that you will have heard of, GDPR, that's coming up, or any kind of other data privacy things that are going around now. So you could also set it up that the data that belongs to users in Europe stays in Europe. The data that belongs to users in North America stays in North America. And you only sync the things between them that you really need to for legitimate reasons. So you could do things like that too. So that's also something that we support. So you don't actually need to sync the entire database between the nodes, you can also just select that you want to sync certain tables. So then you can effectively also set up a sharding system. So that's up to you what your application requires. So one thing might be, I've just been thinking if you have some kind of an ordering system, you might just store the orders locally, because the orders don't need to be synced across the world. It just needs to be local for delivery and logistics. But you could sync your customer database maybe around the world. So customers could be everywhere, just so the local logistics information doesn't have to be synced and also kept for maybe privacy reasons and regulatory reasons and all those kind of things that everyone has to deal with in their business. So there's a lot of options there. So VTR3 is a Postgres extension. So it doesn't. VTR1 used to be, some of you might remember, VTR1 required a patched Postgres. That's no longer the case. So VTR3 is an extension, runs on Postgres 10 or also in the future, whatever comes up. So VTR3 is now rebuilt. It used to be that VTR3 was an entirely separate extension, but VTR3 is now built on another extension called PostgreSQL, which I'll talk a little bit about later. So PostgreSQL is essentially just an extension that does one-to-one replication, which is point-to-point replication. And VTR3 works on top of that. So PostgreSQL provides the replication layer, or the transport layer if you want. And then VTR3 is on top of that, just provides the coordination and the clustering and the node communication. So it's just a better architecture that you don't have to maintain all these different duplicate ways of doing replication. And then we have a couple add-on facilities that you don't have to worry about yet, but we have some tooling around it and a way to assess, like a tool to assess whether your application will likely work with VTR or not. It just kind of checks how many conflict issues you have in the database and things like that. So again, if you are still on older than Postgres 10, it's not going to work. It can't be backported. It's not going to happen. Postgres 11, when it comes out, will be supported. That's not a problem. We have a thing in second quadrant. We have our own fork in a way that's called second quadrant Postgres, which is not, we don't have that because we want to trick people into using that. It's just we do a lot of development on this in this area and others that the community has not accepted yet, or in some cases does not want to accept at all, although that's quite rare. So we put that into our branch, so to speak. Let's maybe not even call it fork, our branch. So you can, or our customers can have it earlier, and then we'll merge it back later. So that's just for some things. We have our own sort of little advanced version in a way, but it's not really it doesn't have sort of totally new features or anything like that. Right? So if you see that somewhere, that's just what that is like. So if you, just a couple days ago, I read a mailing list post of someone who, just on Postgres General or something like that. I've been he was writing, I've been running my server now for 4 years, and now I'm thinking about setting up some applications. So congratulations to you, good luck. I wonder how you've been maintaining your database on all those years. So if you are being a bit more prudent than that, then you might do something like this until now, right? You have a master server, and then you have a couple of standbys that are using the long established now physical replication features of Postgres. That just in case, and then you have a little bit of tooling around that, and then if the main guy here somehow dies, one of the other one takes over. In principle, you don't need 3, but 3 is kind of recommended. But you can make your own choices in terms of how much resources you want. So that's a pretty standard architecture. So what we propose now is for high availability setup or a geo cluster is this system. So you would still use the physical replication systems for your sort of basic local high availability, and then you basically set up the same thing on the other side as well. So if this guy dies, you don't want to fail over to your remote side. You still use those local systems as your backup, but then you still have the same thing in the remote side or different availabilities or something like that. So I was mentioning we want to also use or propose VTR for what we call very high availability. If you use a system like this one, which many or most of you are using now, and something fails, it could, it's pretty quick now, and many years of effort have gone into this, but having a failover or a switch over on that can take many seconds, sometimes minutes, depending on how you set it up. And there's many ways to tweak that. But and sometimes that's okay. In many cases that's okay. But if you don't want to take a minute, then you have a problem, and you can't really use that system. So what we're proposing now with this system is that you have, and what we call this in our kind of literature is we have a lead master and a shadow master, and they're both masters really, but you have they're both connected to BDRs by BDR to each other, and you use the connection router here, and what we're using is HA proxy, but you could use something similar that just routes connections around. And your application just writes to that one, and when there's a problem connecting to it, we just, the connection router will recognize that very quickly, and then you just start writing here. You don't need to wait for any promotion or switch over really in the traditional sense. You just start writing immediately because it's a master you can write to it. And if this guy is still processing something, if just the network goes down here and this guy is still processing, it will replicate and eventually synchronize. And then if for some reason you wanted this, maybe guy comes back and you want to switch back, you just immediately your connection router software just switches back over and starts writing here. So you can just go switching back and forth like all the time basically, and there's no reason not to. As opposed to the existing physical applications setup where if you've ever also done that and worked on the low level there, switching back and forth is fairly complicated, and you have to use things like PG rewind and about like timelines and all that stuff. There's tooling around it, but it's complex, and this is basically, there's no complexity here at all. You just write to that guy immediately. So you have, obviously there's also a split second while the network can readjust itself and all that kind of stuff. So it's not actually immediate, but it's really quick. Mainly depending on your network setup, really, not really anything to do with the database. So that's what I mentioned in the beginning, what people have always been asking about us for the VTR1 architecture, which couldn't really do this so well, but now this is possible. So this, if you do this entire setup, you kind of mix two different replication systems in Postgres, and those of you who work with Postgres will kind of be familiar with them. So there's physical application, which does straight wall, right-hand wall copying, and that's very good for the local HA. And then the logical replication is more bandwidth efficient in a way, and also release neutral, so you can use it for upgrades, and that is better for the remote HA. So you can combine that. And actually, VTR also has this smarts that if this guy dies, let's say you have a logical link between logical application link between these two different sites, and this guy dies, you switch over to this one here as the local physical master. The logical replication state is actually sort of communicated between those two, so that guy can just continue the replication to the other side immediately. So that's also something that's not available in just stock Postgres right now. So what happens here? There's obviously these obvious questions with distributed systems. What happens if you have a problem on the network? You can still use the databases on both sides. And when the network comes back, they just sync the data. So there's obviously a point if the link is down for a long time, both of these sides have to keep the data that is not yet replicated around, right? So they have to store that on disk. And eventually when the link comes back up, they might have a lot of stuff to ship over. if the link is down, indefinitely, basically, then eventually they're going to run out of disk. So there is sort of a limit to how long you can play this, but in practical terms, this is not a problem. It might be a problem for your business if the link is down and you don't have the information, right? But for the integrity of the database system, it's not a problem. So in this case, I already explained, if one of the nodes goes down, you can just do a switch over to one of the other nodes. All the information to know how far the application has gone with the other nodes is communicated between all the nodes, so that just works. So we have, while designing this, we have looked through all the cases of downtime that amongst our customers or users that we could find, and architected the system to handle it. So well-known cases of host is down or network is down, I just explained, that's pretty easy. And there's maybe also the case of what happens if the replication software fails. That is in a way also accidentally covered in this architecture because there's two different ways replication is happening, right? There's this physical way and this logical way. So if there's a bug in this one, this is still going to keep working. So that's not really, we don't design software so it can handle failures in the software itself. Like, that's also kind of a nice property of the system. But one thing that's actually kind of becoming more relevant is that as sources of downtime, really, obviously hardware failures and network failures happen, but more frequently because of downtime, also this voluntary downtime of people doing system maintenance. Just especially with sort of really renewed focus on security, what a lot of users are doing now, they're just doing sort of like scheduled system upgrades, and in some cases they do something apparently this is a term I didn't know either, they do something what they call a rehydrate, which they essentially detach the storage and then rebuild the operating system from scratch. So you can obviously do this now much easier with sort of images and Docker and those kinds of things, so that's not actually a reinstall, but they build the operating system from scratch using latest sort of packages and sources with presumably all security patches, and then reattach the storage. And they do this on some kind of schedule that they set based on their own requirements. Or just other sort of general upgrades in general, major operating system upgrades, major Postgres upgrades, and those are really sources of more significant sources of downtime that also build into the business processes or business requirements, not necessarily these sort of more accidental sources. So this is fully supported here. You can, it's basically kind of like that, right? You can just take the node down, replace it with a different one, bring it back up, it syncs it back up. So this is fully supported here. And logical replication in Postgres is version agnostic. So if you just want to upgrade them from 10 to 11 or 12 in the future, that is also fully supported. So if you have this asynchronous replication system, you have to think about conflicts. Or maybe you don't, because the software does it for you, but the software has to think about it. And so there are a couple variants of conflicts. So one conflict possibility is the insert conflict, that two clients or two users insert the same thing in different nodes, and then when these nodes are consolidating their data, then what do they do? Right? You use order number 1, 2, 3, 4 here, and then there's order number 1, 2, 3, 4 over there. What do you do? So you have to think about that. And then there's a variety of other combinations. What happens if somebody changes something over there, and to maybe changes the price of something, of the item, and then someone else changes the price of the item to something else? What do you do? And so there's also a more complicated version of that, but that's sort of the basic idea. So this system sort of addresses the insert conflict by, you can address that yourself by using UUIDs, right? Instead of relying on sort of a counter, you use the UUIDs that are generated sort of in a random way, or there's sort of various ways to do that. That's good, and it is a sort of a reasonable approach, but UUIDs in databases are not sort of the most efficient way to do some things, because because they're completely randomly generated, they don't really sort of cluster well on indexes. So if you have sort of create multiple order items or something like that in sort of a sequence, you kind of want to have them, you want to have the IDs that you give them close together, so then later on you can use more efficient sort of indexing mechanisms or things like that, right? So that UIDs don't work so well with that. They work, but they're just not as efficient. So what we have implemented in VTR is our global sequences. So Postgres has local sequences that just give you numbers, and VTR has global sequences that put the node number and the timestamp into the sequence. So this is something you might have heard the term KS UID, K-sortable UID, and it's a kind of a standard mechanism essentially. So that you put the node number, the timestamp, and then the local sequence counter into a 64-bit integer essentially, and that's your number. So that way, because you have the node ID and the sequence counter, you essentially have no conflicts, and then if you put the timestamp in there, it's just kind of sorting a little bit. So that's a standard technique. That's what we also use here. So that helps with the insert conflicts, and then if you have update conflicts, we have a variety of conflict resolution mechanisms. That's already been available in all the VTR and physiological versions. So the default in this default setting is last update wins. There's also other versions of first update wins, or remote update wins, or local update wins. So that kind of depends on the business requirements. But usually the last update wins is the one that ends up making most sense. And there's also the possibility to plug in your own conflict resolution mechanisms by writing a little function to hook it in. It sounds very attractive, but it's very dangerous, because you have to make sure that it resolves the conflict in the same way everywhere. You can't just say, local wins. You can't just say my node wins. You have to somehow arrange it that then the other node also thinks that the other node wins, right? You can't just, you have to really think this is quite dangerous. So the built-in mechanisms are usually better. But essentially, this is all taken care of. Now, before we move on, there is because of this, this is a distributed system. And the problem is that you can't just take any old database application and have it run on this and just work. Because you have to think this through. What happens if someone does this and then someone does that? You have to think through these scenarios. And what happens if you have a lot of just the way some applications are architected, they just have like write conflicts all the time. And they're just probably going to have trouble mapping that to any of these conflict resolution mechanisms. So there is sort of a necessity to evaluate an application whether it's sort of fit for this. So that's sort of the bad news. The good news, or sort of the good news for some, but bad news for others, is that usually an application that doesn't work on this distributed mechanism is also already in trouble locally. Because those are the applications that are just kind of writing the same row everywhere, and you have a lot of conflicts, even just on the local writes, and those are the kind of applications that are just in trouble already and are not going to be happy and can't scale. So an application that works well locally and avoids sort of write conflicts locally is already going to have work much better locally, but it's going to be able to migrate to a distributed system much better. And we have some, we have sort of offer consulting and stuff like that, so you can evaluate that if you're really interested. So there is a lot of you will have heard of the cap theorem, right? That's just something that's being thrown around in distributed systems. So CAP is you have to choose two of consistency, availability, or tolerance of network partitions. And since you can't avoid network partitions entirely, you have to essentially choose between availability and consistency, right? That's the cap theorem. So that's what happens if you have a network partition. So if you have trouble, then you have to make choices. there's another theorem which is, or sort of, yeah, I guess it was a theorem, it's the PAC-ELK, which says, so the PAC-ELK is, the PAC is actually the same as the CAP. So what that says is if you have network partitions, then you have to choose between availability and consistency, that's PAC. But even then, well, the E is else. So even if you have no network partition, you have to choose between latency and consistency. So even when everything's going fine, you have to kind of choose latency or consistency. And VTR can do consistency, but what that requires, and it requires basically all the nodes to have some kind of way to talk to each other to make sure they all agree on what's going on. And there's a protocol, there's a couple of protocols, but what VTR uses is a protocol called draft. And some of you might have heard of that too, which is used so the nodes all talk to each other and agree what's going on. That takes a lot of round trips and it's very slow, and it's usually not what people want. So what the default mode is in VTR is here basically what most people don't want is the latency, so they give up the consistency to avoid latency. And this is the default mode in the distributed system like VTR. So you write locally, quickly, avoid latency, and then but you don't get the up-to-date data, which is what consistency means. So you kind of have that trade-off that you can write fast and read fast, but you might not have the absolute latest data, and then the nodes sort of work that out later. So what's cool about VTR, just to kind of summarize that, it's not the first multi-master system with Postgres in the world, but I think it's the best one, and it's the most sort of the one that is built, it is an extension of Postgres, but it uses all the facilities that have been put in Postgres core for this very purpose. So it doesn't use triggers or it doesn't use any hacked Postgres, it just uses the facilities in Postgres that are meant for that. And it's very high availability, as I mentioned, so instead of having, you can count your 9s here that you want. If you have to do a couple of failovers a month, you have downtime in the minutes. If you use this system, you just rely on the network reconfiguring itself. You might have just downtime in seconds or even minutes. That depends. And VTR does DDL replication in case you're interested. So it means like if you create a table, it's automatically created in all the nodes. So that's just a side point. And it has global sequences as I described. And this is our sort of Salesspiel here, right? We've been developing this stuff for many years, and so we know how this works, if you want to talk to us about this. So any concerns, perhaps, that sometimes people go, oh, yeah, because it's just sort of, we're anticipating this, right? But we haven't really had a lot of sort of negative feedback about this. So. The confusion there is that the C in ACID is not the same as the C in CAP or PAC-ELK, right? So this is not a valid complaint, it's not ACID compliant. You can't have an ACID compliant database system. Or the PAC-ELK theorem basically says if you want to have an ACID compliant database system, distributed system, you're going to have terrible latency and it's not going to be useful. So that's the trade-off we make. We have some tooling around this. If you think it's difficult to operate, we also have our own sort of cloud service, which is called GDS. We can host that for you and operate it for you. And it's not currently open source. We plan to open source it later. We have tried to open source it in the past and tried to feed things into Postgres core. It's just been very difficult. And at this point, we just want to get working software out. So we're not open sourcing that at the moment. It is very scalable, so we have track record of that, and we have tooling. So these are just kind of invalid concerns, so to speak. So this is a chart I've shown before at a previous meeting. We have even though it's an extension, the amount of work that we, my colleagues, and even others in the Postgres community have put into feeding all of this stuff into Postgres core is extensive. So we have this project is started around the time of Postgres 9.2, and just a whole bunch of features have been put into Postgres 4 to support application systems such as this. And you don't have to read them all, but these are all sort of these low-level features that you might have heard of here and there in technical documentation. So there's event triggers, background workers, replication slots, logical decoding. There's commit timestamps, replication origins, and so on and so on. So this is all the work that we had sort of a fork initially, and then we have just fed all these features back into core, so we can build a replication system as an extension on top of that. And we're going to continue doing that. So this has basically been our mode of operation for many years now, that we keep building our application solutions based on what we think, where we see things going and what customers want, and then either we build them in the extension, or if it can't be built in the extension, we put things in Postgres core, and if somehow we can't get it into Postgres core, we put it temporarily into our own branch, as I explained previously, and then we keep feeding stuff back into Postgres core. So, because we don't want to keep maintaining this stuff on our own forever, right? The Postgres community is very strong, and a lot of smart people in there. So the more stuff we can sort of put into the common hands, the less sort of maintenance we have in the long run. So there's another tool that we developed at Second Quadrant. It's called MEBE, which is a graphical database management tool. Very similar to others you might have heard of. And that supports Postgres, obviously. Supports these other projects too, other products too, if you kind of have a mixed environment. That's kind of useful for that, and we'll also have VTR support. So if you're just using VTR and OmniDB, then you'll have an extra tab, and you can manage that. So that's kind of cool too. So that's OmniDB. If you want to look for that, omnidb.org. It's just a very simple download. Works on Linux, Windows, Mac. It's quite nice. This is kind of the timeline of what we're doing. We announced VTR3 in May, so it's still May, and then we're going to start shipping in June. And we're going to keep, we have a pretty aggressive timeline in terms of features and stuff we want to do, and so there'll be a bunch of new things coming out on a monthly basis. So here's our website. There's actually a webinar later this week, which is going to be very similar to this, so you don't really need to see that unless you kind of didn't remember anything. And we have a white paper too if you're interested in more technical details and stuff like that, right? So this is marketing stuff. These are a couple of things that we're working on, and this is sort of more general of like where do we see replication stuff going in Postgres, or distributed systems going on in the Postgres ecosystem. Some of this stuff will go into Postgres core, some of it will go into VTR, some of it will go maybe into Visualogical, just depending on sort of some technical decisions. So there's, right now, all the update conflict handling is on a row basis. So either that row wins or that row wins, and we want to work on splitting that on a column basis, so that maybe for a certain column, the latest one wins, but for a certain other column, maybe the local node wins, so you just kind of split that up. So that's probably pretty straightforward, but you just have to kind of do that. More interesting are the next two items, which are sort of, consider the case of a counter, right? You have maybe two remote nodes, and you increment a counter here, you increment a counter there, and then you do conflict resolution. It doesn't matter what mechanism you use. Basically, the way the conflict resolution works is essentially this one wins or that one wins, and then the result is the counter has been counted at once. So you lose one update, right? The way to sort of fix that in a traditional database system is that you use a bunch of, like, this is a classical case even in a local database system, and then you use all these asset properties to kind of fix that, right? So the way to fix that is that you use locking on one guy, and the guy has to wait until the other one finishes, and then the second one comes up, right? That's a classical database problem. But in a distributed system, we don't want to do it that way, because that just requires like global locking, and that's terrible. So there are some mechanisms to do that you basically declare the column or the data type in a certain way and say this is the sort of the third item, CRDT. This is a kind of a standard sort of term of stands for conflict-free replicated data types. This is sort of a special data type, or a group of special data types that have additional properties that so they can consolidate these kind of situations where you say this is a counter. So if you have if you increment a counter and you have 2 increments, and then you can consolidate those 2 increments to have n plus 2. And there's a couple other variants of that. You could have maybe a set type, for example. So you add something to the set here and add something to the set there, and then they have a way to essentially a merge operator between those 2 types, and then the merge of the 2 sets is then just a union of those 2 sets instead of picking one or the other. So that would kind of fix that situation. The other delta change updates is a bit harder. That's the situation where you increase the price of something, right? You add 20 here and you subtract 5 over there. The CRDTs are not going to fix that because that's just kind of outside of that domain. So you would have to somehow have some really specific smarts in there to consolidate, the plus 20 versus the minus 5. What do you want to do with that? And then, so that'll be harder, but that's something we want to work on. And there's, the multi-node consistency. That's kind of the applying to the geo-sharding use case I showed earlier, that you want to only replicate parts of your data around and keep other stuff locally, either because it's just too much to ship around, or you have maybe some regulatory reasons. So there are the mechanisms where you can do global queries across everything, which are not going to be fast, but sometimes you want to do that, right? So that's something to work on. That's not really very close, I think. And obviously performance is always important. So this is kind of what we have on the roadmap for this year and next. And again, a lot of this will probably end up in PG Logical, not actually in VTR proper. So that's VTR. So now, just to kind of wrap it up a little bit, or address maybe that's something that will be more immediately available to many of you, is PG Logical, which is sort of the underlying transport layer of VTR, but it's also a very useful and powerful extension of its own. It just does one-to-one replication, right? So it doesn't have any sort of global awareness of how these things are wired together, but it just replicates completely. And that works all the way back to Postgres 9.4, so you can also even use it for upgrades from old versions and things like that, or just replicating between old stuff you have lying around to something newer, or it's basically, in this case, kind of up to you to what to do with it and why not. So here's a bunch of like why this versus, well, doesn't Postgres 10 have built-in logical replication? Yes, and it's nice, and I worked on that myself, so he's used that. But essentially, that functionality in Postgres core is one of those cases where we took what we developed on our own and kind of fed it back into Postgres core. So that is essentially what's in Postgres 10 now is a subset of what we had developed externally in PG Logical. And here's a bunch of things that PG Logical does now that is not in core or in core yet. So these are also potential candidates to put back into core at some point. So it supports older versions, obviously. It has a bunch of more functionality for row and column filtering, some DDL replication, and sequence replication, and truncate replication. Although the asterisk there on truncate is truncate replication we actually put in Postgres 11, which is coming out later. And PG Logical has the conflict resolution that I mentioned, so first update wins, last update wins, all that stuff is in PG Logical. And the failover support, which is always sort of hard to understand, but important if you have such a mixed architecture, that you have some physical replication combined with some logical replication, as we had earlier in the VTR architecture. So if you have a couple of, a pair, let's say, or 3 nodes connected by physical replication just for your local basic HA. But hanging off that, you have a logical application maybe somewhere else, geographically remote, or for archiving or some analytics or anything like that. If you have a failover on the physical pair, because one node goes away or you have to take it away or something like that, previously, then your logical application is broken. Because the progress information for the logical replication was not saved between the physical replication. So then you'd have to just set that up from scratch. And that's obviously terrible. So that was fixed in PGLogical 3 with Postgres 10. So I know there's a lot of versions here of like it's in this, we have this even in our day-to-day work when we do Postgres development consulting and stuff like that around this. This works with that version, but if you use it with that version, it can do this on top of that, but only if you use it with the new Postgres version. And that's just, I'm sorry, that's just the way it is, right? We just keep moving so quickly that certain things only work with certain versions. So PGLogical 3 kind of comes in a pair with VTR3. So that's also the new version. PGLogical current version is 2.2, so that's out there and open source and available, so you can just use that right now. This is coming out later this year. So there's a couple new features. The failover support I just explained, and a couple other things. One thing that's kind of cool is that, or you could argue that's currently a missing feature, but one thing that's kind of cool that PGLogical can do is you can replicate into a partition table, or you can replicate into a view, as long as the view is writable. Or you can even replicate into a foreign table, which means whatever the foreign table writes to, you can replicate into that. So if you have a foreign table that points to a different database system, it could be Hadoop or Oracle or anything like that, you can replicate into that. So I don't know why you would do that. A lot of people would come and ask to do it the other way around, obviously. At least they come to us asking for the other way around. That we don't have a good answer for that, but if you want to replicate away from Postgres somewhere else, then there's options here now. And something else is that PGLogical 3 can actually now write the replication stream in Kafka or RabbitMQ if you want to do that, or you just distribute and change streams around. There are existing systems that can do that. And some of them are not really maintained anymore, so that's been a problem for someone who's been using that. But the advantage here is, again, you can just use the same system that you already know in terms of management and monitoring and stuff like that. If you want to, instead of writing into a table, you can just write to a Kafka or something like that. So, all right. So PGLogical 3 here's again, that's open source out right now. You can just search for that, or it's on GitHub. And PGLogical 3 is going to come out later this year. All right. So that's all I have for all this replication stuff. Some just general Postgres news for those of you who are not following this day to day. So we just had new minor releases last week, I suppose. Yeah. So if you're not using any of these versions, then you need to make some plans, right? If you're still using anything that's less than 9.3, then that's out of support altogether by the community, so you need to think about how to upgrade that. And if you're not using any of these minor versions, then it's not going to go up in flames tomorrow, but then you're just going to be behind all the bug fixes and security fixes. Postgres 11 is kind of in the oven right now. We're planning to release the first beta of that next week. And I don't see why that wouldn't happen, but it looks pretty good right now. So that's going to contain a whole bunch of new exciting features. And that's going to be out later this year, usually sort of September is when these final releases come out. As we had earlier in the sort of question section, we have a release usually every year in sort of September timeframe. And actually, we have a new website. We had a conference in Jersey City, a sort of major Postgres conference of the year in Jersey City in April, and there was a speaker on the stage who actually had this sort of was going on a little bit about how Postgres is sort of very conservative. The community projects are conservative in many respects, and the website hasn't changed in 10 years. And just as he was kind of on stage, actually, the new website went up. So that's when the website was changed for the first time in 10 or 15 years. I don't know what it was. So there's a new website, or there's actually also a Twitter account now if you're kind of into that. If you want to sort of have a lightweight news feed from Postgres, that you can subscribe to that. That's been around for a while, but it's not been used at all. It's just was empty, but now it's actually used. So if you're into that and you just want to keep up a little bit with this kind of information, then please subscribe to that too. And so this is then, to conclude, this is about us, my employer. Second quadrant is a company that does sustainable open source development for Postgres. And sustainable means, we want to give things away, but we also have to make money to finance that. And we contribute heavily to Postgres core and other kinds of things in the Postgres ecosystems. And we make money by providing consulting, and we do 24/7 production support. That's basically our main business. So if you need that kind of thing, you can contract with us, and then you have access to someone 24/7 if there's a problem. And we have other options with cloud hosting, and we have remote DBA and things like that. So if you have Postgres needs, then we could help you. Otherwise, you know where you find Postgres. That's my next slide. Last slide. We're good in time. You could have questions if you want. Was there a question in the back? Yeah.
Yeah.
Just yell loud. I'll try to repeat it.
Yeah, I have a quick question. So the first, I was just curious. What point in time when it's like come in the product pipeline? Because if you guys are basically, for example, if a delete happens after an update happens after a delete, then how do people kind of make sense of all of that stuff?
You're asking about conflict resolution details, like what happens when an update happens after a delete?
Yes.
Well, there's various different scenarios, right? But what happens now is basically if the delete happens first and the update just doesn't update anything, and if the update happens first, then the delete comes and deletes it afterwards. So that kind of resolves itself. But there are obviously other scenarios when you update the primary key and then delete it on the primary key not being there anymore, then you just have some other issues. So changing primary keys usually gets you into trouble with that kind of thing. So there are some details there that I guess we'd have to look through in detail, but that's just basically how it works now.
And then the second question is that if you wanted to do a point in time kind of a thing, so kind of like a database that access to all of the...
I'm sorry, I can't hear that. Can you come a little bit closer? There's a lot of air conditioning going on here.
No worries. So the second question I had is that basically if you wanted to do a point in time thing, so if the database keeps the timeline of all of the events that have been happening, so does the current architecture, can it support it in the future?
If you want to do point-in-time recovery, well, that's already supported in Postgres.
Let's say that you go to a record and basically go into the history of that record.
Oh, you want to do kind of a temporal query?
Yes.
Well, there's not really built-in support. There's no built-in support in Postgres for temporal query at all right now. There are some extensions that kind of fake that in a way by just storing timestamp and having triggers and update timestamp and things like that. But that's not really existing right now. That's actually something that I think me and my team might work on in sort of next year or two. But right now, we don't really have anything for that.
Yeah. And then and anyone can interrupt me because I'll keep.
He's going to keep asking questions. You guys have to.
Yeah. So basically, GraphQL, that's something that came up, and I was really excited about it because I've been using Neo4j for all of my GraphQL needs.
Yeah.
So can this do basically because if you go onto LinkedIn, it's like it can tell you who your friends are between you and some other person through a couple of levels. Can Postgre do something like that?
GraphQL, no, there's not really. I mean, again, you can kind of fake that with other mechanisms, but there's no direct way to do that.
Right. And this.
Eric is going to interrupt you now.
Yeah.
Let's take a question over there.
Yeah, let's grab that question.
We can talk afterwards if you have more questions, okay?
When you say it's multi-master,
Sorry.
when you say the multi-master,
Yeah.
the multi-master architecture,
Yeah.
So is it a really multi-master or a master and shadow? Because if there is a multi-master, there should be
It's a multi-master architecture in the sense that all the nodes in the cluster, let's say, are equally, they're the same, or they have the same properties, right? You can write to any of them. The term lead master and shadow master that we are using here is just basically describes the sort of the very high availability architecture where you just choose to write to one of them, but they're not the same, they're not different technically. You're just going to pick one and use that as the one you write to. But the other one you could write to at any time. That's kind of the point, right?
Do they share the same cache and storage? Because when you say multi-master, they do have...
No, they don't have anything shared. They have no shared cache and they don't have any shared storage.
Okay, so there will be a lot of conflicts going around.
Yes.
Question up here in front.
So you said that you need, for the high availability, you recommend three masters. Is there a point of, well, if you want to do 4 masters because you really want belt and suspended, there's a certain point where it just doesn't make sense to add more, or is 3 start to have a degradation?
So for the very high availability architecture. Yeah, so her question, I'm going to get to the picture. Her question was around this architecture that for the high availability architecture that we are so suggesting that you have 3 nodes there and 3 nodes there. And her question is like, can you add more to have even more sort of higher availability and things like that, right? That was sort of the question.
Like extra redundancy, people that are...
Yeah, even more redundancy. So, I mean, you can always add more, but there's, there's probably not much of a point to that. I think sort of having, if you even read sort of the literature on other database systems and how they, propose their high availability architectures, they usually also require 6 or 7 nodes or something like that. Now you can certainly add more here for just kind of scaling your application, right? That's a whole other aspect to this, that you can add more. So if you have a really read-heavy application, let's say, you can just add a lot more to support that, and that's certainly very common. But for high availability, that's kind of probably the sort of the usual setup here.
One other question.
Yeah.
One of the other slides you show how that you had a connector that it points you to your master lead and then the shadow.
Yeah.
And then it'll automatically fail back.
Yeah.
You configure it to say, I don't want to automatically fail back. I want to manually do.
So the question is, can this particular, like this connection router, I suggested it would automatically switch over, and she's asking if that can also be configured manually. Yeah, this is here basically just HA proxy in this case, and there could be other equivalent pieces of software, but you can configure that in any way you want. But, I mean, obviously the idea of sort of this sub-second, or certainly sub-minute, but sub-second switchover, you can't do that manually, right? So the problem why often you don't want automatic failover is that when you fail over for the wrong reason, sort of fixing that up is very difficult, and you just kind of create a mess, and you can't easily switch back. Whereas in this case, there's really no problem, because both of those masters, or as we just kind of mentioned, they have the same technical properties. You can write to any one of them, really. The only reason why you don't want to randomly write here and there is because then you potentially create conflicts that you don't need otherwise. But if you are setting this up with manual failover, you could do that, but you're probably missing out on the best parts of it.
I was thinking of a scenario like if one of them, your main one starts, there's something flaky with that one, and you end up getting some latency because it keeps on switching back and forth.
Yeah.
But I guess you could put a counter into your setup that if it fails over this many times in a minute, don't.
Yeah, if you have flakiness in any system like this, then there's probably going to be problems, right? I mean, you can make a binary decision of this is down and I do this now. But if you have flakiness in the system and it just things like now it's up, now it's not, and then yeah, you need to have some kind of monitoring around that and probably do some manual decisions.
Question in the back.
So,
Right.
I know you touched briefly on 4 major cloud platforms. So, now categories of elements. You got your Microsoft, you got your IBM, you got your so how would someone who is who has one foot on the business side leverage this in terms of cloud platform?
Okay, so the question there is, I briefly mentioned the major cloud providers earlier, and he's asking how would I leverage this on a sort of cloud environment?
Well, you'll tell me.
Well, okay, so the easiest.
Is that a distinction without a difference, or do you see any value?
Well, a lot of these cloud providers, they are running sort of patched up Postgres that feed into their own sort of backend storage system that is sort of replicated, and there's a lot of magic going on that is, we don't know what is going on there. And they have snapshots and this and that, and they manage all of that automatically for you, which I don't know all the details of that because I just see the same thing that you are seeing. If you would like to have this in the cloud, we have a service for that, which is called, I just briefly mentioned, it's called GDS. It doesn't matter. So you can, we could essentially host that for you on any of those cloud providers. So that's one. Or you could host that yourself on any of those cloud providers, and just instead of running their hack Postgres, you run stock Postgres with this on top, and set up all the monitoring there. So that I think that's kind of the best way forward with that. Or you can, you can run it on-prem, as we say now.
And by all means,
I don't know if this really answered anything,
I'm not trying
but
to set you up to explain how awesome your service is versus the cloud services. How would you characterize the difference?
oh, that's good. Okay, so how would I characterize the difference between this and what the major cloud providers are offering in Postgres? So essentially, the cloud providers don't have multi-master Postgres. They have all kinds, they're good in other ways in terms of, backing up your database and allowing you to click and provide additional, physical standbys, but they don't have any functionality that is really similar to this. The only thing that is maybe similar to this is if you use RDS Aurora, who I believe we're just recently announcing multi-master capabilities. But that's, then you're only using 50% Postgres, and the storage layer below that is something entirely different. And so you're using sort of half a different system. And you can compare those just as you would compare totally different systems. But I don't think anything that the cloud providers are offering right now really has these capabilities. Maybe, in terms of sort of management, but not in terms of high availability, and also certainly not in terms of having sort of widely distributed databases.
That was a complicated question and a complicated answer. I understand.
Okay, so the short answer is you should compare that yourself. Question there, yes. Yeah, no, we'll get to it.
Okay. So you explained how application was for writes using this DDR thing.
Yeah.
Right? And my question is, so one thing you didn't talk about is how reads interact with all of this. And I guess so reads in Postgres, right, as in other databases, they have a lot of stuff. They have timestamps, they have read logs, and some of these things are kind of tied to the server that's serving them, right? So my question is, in one of these multi-master setups, if I ask for the highest type of consistency for my writes, if I say that I want my replication to be consensus-based when using graph, as you mentioned, right? Can I still get serializable transactions from the database? Can I still set my isolation label to serializable and get those guarantees?
So the question is, if you are choosing so we had this brief discussion on latency versus consistency. So if you choose consistency, do you still have choices of isolation levels and things like that? So at the moment, no, we're not nearly as to that point. But there are some, again, these are just thoughts now that we have been having, and then some plans around looking into these kind of problems. But right now, you basically get to use the the C term there. You get basically technically the inconsistent view, and then there's a lot more work to be done to.
But then in terms of so forget us in terms of the isolation level scale, how do you characterize the guarantees that are given? Or is that now?
Well, if you don't even have, if you want to characterize it, you don't even have consistency technically, then it's not really makes sense to talk about isolation levels. But maybe that's a technical discussion that's a little bit beyond what we have to have here. So basically, I don't think we're really at that point to really characterize that. But good point. That's certainly there's a lot of work to be done here. Yes, please. I'm sorry, I have to come a little bit closer.
Perhaps an elementary question, but what's the lowest level of conflict resolution? Some kind of a database level, or is that?
So what's the lowest level of conflict resolution? Conflict resolution always works on a row basis right now, and you can set that either globally or on a in PG Logical you can set it on a per subscription basis. But basically, when you use PDR on top of that, there's only one subscription active, so it's basically globally. So, but on a technical level, it works on a by row basis. So you essentially could tweak it, even on lower levels. But that's sort of the configuration that's exposed right now.
We have time for just one more question.
Yes.
I'm sorry. You first.
Okay. There is one slide in which you are showing the data privacy.
Data, yes.
Yeah. So what kind of things you have?
Data privacy. Well, okay.
Something like a generalization, separation, or differential privacy.
The point he's asking, I mentioned data privacy briefly. I mean, it's obviously the whole subject of its own. What I was referring to here is that you can use systems like this to keep certain data in certain locations for regulatory reasons, perhaps. Like there's other, that doesn't really give you data privacy in the sort of the absolute sense, but you can satisfy, or at least the intent when I wrote that slide was, you can satisfy data privacy regulations that, especially are coming up now, that by keeping certain data in certain locations, whereas you can then maybe other data you want to share around.
So that's belong to the aggregation and generalization function. And for differential privacy, we need to set up the epsilon parameter for that.
I don't think I really know the details of what you're talking about now. That's a different. I'm not even sure what he's asking right now, but this is not really a system to enforce data privacy.
Okay.
That's you can, if you want to have that kind of stuff, that's a different system that can work with all of this.
In simple words, suppose you have data, lots of data with you. In single query, okay, you have lots of data with you in your database. In single query, you cannot find the exact data which you require. That is, you somehow masking your data. But with the aggregation and some kind of function, I do able to find that kind of data.
That's outside of the scope of this system.
Okay.
Did you have your hand up before?
Oh, yeah.
We could maybe
Do we have time for one
absolute last question here.
Yeah.
Just wanted to know if you have a different kind of sharding techniques other than geo sharding.
Other kind of sharding techniques in Postgres, I mean, there's obviously extensions that really kind of make a business around this. So maybe, things like Citus, they kind of do a whole different thing on top of that. What's happening, or there's extensions like, or forks like PostgreSQL that are like more sophisticated than that. And they also do global query and stuff like that. What's going on in Postgres core right now is that we have the ability to do foreign tables in a partition hierarchy. So then these foreign tables, each foreign table maybe would point to a different host. So you could also have sharding that way. That's kind of what's currently going on in core. But then there's extensions and sort of business opportunities there, I guess. Alrighty.
All right, that's all the time we have for questions right now. I want to remind you all, though, that Peter will be here for one-on-one questions right now. Feel free to come on up and ask. Thank you all for coming. Thank you, Peter Eisentraut.